The closest star system to Earth after our Sun lies just over 4 light-years away. It is called Alpha Centauri. At first glance, that distance may not sound extraordinary. After all, light itself covers it in just over 4 years. Yet when we begin to compare that speed with what human technology can achieve, the picture changes quietly but dramatically. Light moves at nearly 300,000 kilometers per second, while even our fastest spacecraft operate at a tiny fraction of that. At those speeds, the same journey would stretch across tens of thousands of years. So when we say Alpha Centauri is our nearest stellar neighbour, we must understand what near means in astronomy. It is a term of comparison, not convenience. Within the scale of the galaxy, 4 light-years is indeed close. Within the scale of human capability, it is almost unimaginably far. This gap between physical distance and technological ability defines the real challenge. Every major journey in human history, from crossing oceans to reaching the moon, extended our reach by improving tools we already understood. Interstellar travel demands something different. It requires us to operate in a domain where even our best technologies are insufficient. Consider a simple comparison. If the distance from Earth to the moon were reduced to 1 meter, then Alpha Centauri would still be over 10,000 kilometers away. That is the difference in scale we are dealing with. This is why a mission to Alpha Centauri is not merely another step in exploration. It represents a shift in kind, not just degree. We are no longer talking about visiting nearby worlds, but about leaving the solar system entirely and sustaining life across interstellar space. And that leads to a fundamental requirement. Before attempting such a journey, humanity must first learn how to live away from Earth for extended periods. Not for months as on the International Space Station, but for decades, even generations. A stable presence on the Moon, on Mars, and in artificial habitats becomes a necessary foundation. A useful teaching insight here is this: exploration follows stability. Civilizations expand outward only after they secure reliable systems for survival. Without that, ambition collapses under its own weight. So the question is not simply how we reach Alpha Centauri. It is when humanity becomes capable of even attempting it. And behind that lies a deeper consideration. What kind of civilization builds a ship knowing its destination lies beyond a single human lifetime? That question will guide everything that follows. One of the most common questions people ask is surprisingly simple. What would it actually take to travel to another star? It sounds like a question about engines or speed, but as we begin to examine it closely, it becomes clear that the answer is much broader. The challenge is not defined by a single invention, but by a set of capabilities that must come together at once. Traveling between stars is not just difficult, it demands progress in several fundamental areas, each of which acts as a gate. Unless at least one of these gates is opened, the journey remains out of reach. One possibility often discussed is faster-than-light travel. In theory, it would compress vast distances into manageable timeframes. However, current physics offers no confirmed method to achieve this. So while it remains an interesting idea, it cannot yet serve as a practical foundation. A more grounded path lies in energy. Interstellar travel requires enormous amounts of it. To accelerate even a modest spacecraft to a fraction of light speed would demand energy comparable to the total output of entire nations. This leads to a simple teaching insight. Distance is not the only barrier. Energy is equally decisive. Then there is the role of artificial intelligence. Managing a mission that lasts decades or centuries involves continuous monitoring, repair, and decision-making. Human crews alone may not be sufficient. Advanced AI systems could act as long-term custodians, maintaining stability when direct human control becomes limited. Another requirement is near-perfect recycling. On Earth, we rely on constant external inputs. In deep space, there are none. Every drop of water, every molecule of air, and every unit of waste must be reused with extreme efficiency. Even a small loss, repeated over decades, becomes unsustainable. Human biology also introduces constraints. A journey that exceeds a single lifetime raises difficult questions. One solution is stasis, placing humans in a suspended state to reduce aging and resource consumption. While still experimental, it represents a logical response to the limits of lifespan. Without at least one of these capabilities reaching a high level of maturity, interstellar missions remain impractical. This is not a matter of ambition, but of thresholds. Yet even within our current understanding, there exists a more immediate, if imperfect, approach. It does not rely on new physics or speculative breakthroughs, but on extending known principles to their limits. That approach is nuclear propulsion. It may not be elegant, and it certainly raises serious challenges. But it establishes something important: a baseline, a point at which interstellar travel shifts from impossible to merely difficult. And from that baseline, the first true interstellar engines begin to take shape. From that baseline, the idea becomes more concrete. If we set aside speculative breakthroughs and work only with principles we already understand, one concept stands out as the first serious candidate for interstellar travel. It is known as the Orion Drive. At its core, the idea is surprisingly direct. Instead of relying on a continuous engine, the spacecraft would be pushed forward by a series of controlled nuclear explosions. Each detonation occurs behind the ship, and the force is transferred through a large, shock-absorbing structure, gradually building velocity over time. A simple way to visualize this is to imagine a boat being pushed forward by repeated waves. Each wave adds a small amount of momentum. Alone, each push is limited. But repeated thousands of times, the effect becomes substantial. In the case of the Orion Drive, those waves are nuclear detonations. The scale is vastly different, but the principle remains the same: momentum accumulated step by step. With this method, calculations suggest that a spacecraft could reach speeds of roughly 3% of the speed of light. That may sound modest, but in interstellar terms, it represents a significant threshold. At that velocity, the journey to Alpha Centauri would take on the order of 130 years. This introduces an important teaching insight. In space travel, speed is not judged in absolute terms, but in fractions of light speed. Even a few percent can transform an impossible journey into a generational one. But propulsion is only one part of the picture. The spacecraft itself would have to be enormous, far beyond anything humanity has built so far. Estimates suggest a structure weighing hundreds of thousands of tons, designed not just to travel, but to sustain life for over a century. This changes how we think about the vehicle. It is no longer simply a ship. It becomes a self-contained environment with its own ecosystems, repair systems, and internal stability. In practical terms, it functions more like a small, isolated world. And here, the challenge becomes more subtle. Over such long durations, even minor failures accumulate. A small mechanical issue, a gradual loss of materials, or a failure in life support systems can grow into critical risks if not continuously managed. Deep space offers no opportunity for external assistance. There are no resupply missions, no quick returns, and no margin for neglect. Reliability must be built into every layer of the system. So while the Orion Drive demonstrates that interstellar travel is physically achievable, it also reveals a deeper truth. Reaching another star is not only about moving through space, it is about sustaining a functioning world across time. And that realization shifts our attention from propulsion alone to something equally important: why such a journey would be undertaken in the first place. And once we accept that such a journey is technically possible, another question begins to surface, one that is often misunderstood. Why would we go at all? Popular imagination tends to frame interstellar travel as an escape plan, a final option when Earth becomes uninhabitable. It is a compelling idea, but it does not hold up under closer examination. Consider the scale of effort we have already discussed. A starship capable of sustaining life for over a century would require immense resources, coordination, and precision. Now compare that with the challenges we face on Earth, even in extreme scenarios. Environmental damage, climate instability, or even large-scale conflict are serious problems. But they are localized within a system we already understand. Earth remains a place where resources exist, where gravity, atmosphere, and ecosystems are naturally available. Repairing a damaged environment, while difficult, is still far more practical than building a completely self-contained world and sending it across interstellar space. A useful way to think about this is through effort versus outcome. If a civilization can invest the energy required to leave its star system, it almost certainly has the capacity to solve most problems within it. There are, of course, exceptions. Certain extreme and highly unlikely events could change this calculation. For example, a massive astrophysical threat, such as a rogue black hole entering the solar system, would alter conditions so fundamentally that remaining on Earth might no longer be viable. But such scenarios are rare and unpredictable. This leads to an important teaching insight. Interstellar travel is not driven by urgency, it is driven by capability. Throughout history, expansion has followed stability, not collapse. Societies explore new territories when they have surplus resources, not when they are on the verge of failure. The same principle applies here, but on a much larger scale. So if humanity does build starships, it will not be out of desperation. It will be a deliberate choice, made from a position of strength. An extension of curiosity, growth, and long-term planning. And once we frame it this way, another layer of the problem becomes clear. If this is an act of expansion, not escape, then it must also be supported by something equally large in scale. Not just technology, but an economic system capable of sustaining such an effort over time. Because before any starship leaves, it must first be built. And that immediately brings us to a constraint that is often underestimated: economics. We tend to think of space travel as an engineering problem. In reality, it is equally a question of resource allocation. Every material, every system, and every layer of redundancy must be produced, assembled, and maintained at scale. That scale is difficult to grasp until we translate it into familiar terms. Estimates for an Orion-class interstellar vessel reach into the range of several $1 trillion. To place that in context, this is comparable to a significant fraction of the annual economic output of a major nation. And this figure applies to a single ship, not an entire program. A useful teaching insight here is that cost in such projects is not driven by distance alone, but by duration and independence. A spacecraft that must operate for over a century cannot rely on external support. It must carry its infrastructure with it. In effect, it is not just transporting people, but transporting an entire functioning system. This leads to an important implication. No single institution, and likely no single nation, could reasonably undertake such a project in isolation. The effort would require either sustained global cooperation or a future economy that extends beyond Earth, where resources can be gathered and manufactured throughout the solar system. There is also the question of risk. In interstellar space, failure is not a temporary setback. It is final. This changes how missions are designed. Rather than relying on a single vessel, multiple ships would likely be constructed and launched. Think of it as a fleet rather than an expedition. Each ship increases the probability that at least one will successfully reach its destination. Redundancy, in this context, is not inefficiency. It is a survival strategy. Even within each ship, systems would be duplicated, sometimes several times over. Life support, propulsion control, structural integrity systems, each must continue functioning despite wear, damage, or unforeseen events. This creates a layered approach to reliability. If one system fails, another compensates. If one ship fails, another continues. Over long timescales, this kind of redundancy becomes essential, and this is where the economic perspective becomes inseparable from the technological one. A civilization capable of supporting such redundancy must operate at a scale far beyond our current industrial limits. Which naturally leads to the next step in our understanding. If building starships requires such immense resources, what kind of civilization would be able to sustain that level of production continuously? To answer that, we must expand our view beyond Earth itself and consider a civilization that is no longer confined to a single planet. To support an effort of that scale, the structure of civilization itself must expand beyond anything we see today. A society capable of building interstellar starships would not be confined to a single planet. It would extend across the solar system, using the resources of multiple worlds, moons, and asteroids. This is not a speculative leap, but a practical progression. Earth alone does not contain the accessible materials or energy required for continuous large-scale production of interstellar vessels. Consider the abundance of raw materials in the asteroid belt. Even a single large asteroid contains more metals than have been mined throughout human history. With sufficient automation, these resources could be extracted, processed, and assembled into structures far larger than anything built on Earth. This is where artificial intelligence becomes more than a support tool. It becomes an industrial partner. Autonomous systems could operate continuously in environments unsuitable for humans, converting raw matter into usable components. Over time, this allows production to scale without the limitations of human labor. Energy, too, changes in character. On Earth, it is scarce and carefully managed. In space, particularly near the Sun, it becomes abundant. Large-scale solar collectors could harvest vast amounts of energy, enough to power manufacturing processes, propulsion systems, and entire artificial habitats. A useful teaching insight here is that scarcity often defines the limits of a civilization. When energy and materials become abundant, those limits shift dramatically. What once seemed impractical becomes routine. In such a system, constructing a single starship is no longer an extraordinary event. It becomes part of an ongoing process. Habitats, transport vessels, and industrial platforms could be produced continuously, each contributing to a growing network of infrastructure. Population scale would also change. A civilization distributed across the solar system could support numbers far beyond those on Earth today, not because of necessity, but because space itself provides room for expansion. And once production reaches that level, the logic becomes straightforward. If a civilization can build large structures repeatedly and reliably, then building ships capable of reaching nearby stars becomes a matter of allocation, not possibility. This leads to an important conclusion. Interstellar travel does not emerge as a singular breakthrough. It emerges as a natural extension of a mature, spacefaring civilization operating at scale. And once that threshold is crossed, the question shifts again. Not whether such journeys can be made, but how they can be made faster, more efficiently, and with greater precision. Which brings us to the next stage of development, rethinking propulsion itself. And as soon as propulsion becomes a matter of refinement rather than possibility, a new direction begins to emerge. The question is no longer how to move through space, but how to do so with greater efficiency and control. The nuclear approach provides a workable starting point, but it carries limitations. It requires carrying large amounts of fuel, generates extreme mechanical stress, and introduces risks that scale with the duration of the mission. Naturally, attention turns toward alternatives that can reduce these constraints. One such path is fusion propulsion. Unlike nuclear fission, which splits atoms, fusion combines them, releasing far greater energy per unit of fuel. In principle, this allows a spacecraft to achieve higher speeds with less mass dedicated to propulsion. The concept remains under development, but its potential is significant. Another approach shifts the problem entirely. Instead of carrying energy on board, a spacecraft could receive it from an external source. This is the idea behind laser propulsion and energy beaming systems. Powerful lasers positioned far from the spacecraft would direct energy toward it, gradually accelerating it over long distances. A simple way to understand this is to imagine a sailboat, not pushed by wind, but by a continuous beam of light. The sail does not store energy, it receives it, and as long as the beam remains focused, acceleration continues. This principle is already being explored in early-stage projects. Small-scale probes, far lighter than crewed ships, could be accelerated to a significant fraction of the speed of light using this method. While these probes would not carry humans, they demonstrate that high-speed interstellar travel may not require carrying all resources from the start. A useful teaching insight here is that efficiency in space travel often comes from reducing what must be carried. Every kilogram removed from the spacecraft simplifies the entire system. Energy beaming takes this idea to its logical extreme. These methods also reshape the structure of a journey. Instead of continuous thrust throughout the mission, acceleration could occur during an initial phase, followed by a long period of coasting through interstellar space. Deceleration, if required, would be handled separately, possibly by another external system or onboard reserves. In this model, most of the journey becomes a quiet passage, governed not by engines, but by momentum. And with that shift, travel times begin to shrink. What once required centuries could, under more advanced systems, be reduced to decades. This progression does not eliminate the challenges we have discussed. It refines them. It changes the balance between energy, mass, and time. Which leads to the next critical decision. If reaching nearby stars becomes increasingly feasible, where exactly should we go? Because not all destinations, even the closest ones, are equally suitable for human exploration or settlement. And once faster and more efficient propulsion brings nearby stars within reach, the focus shifts to a question that is less obvious, but equally decisive. Where should we go? At first, the answer seems straightforward. The nearest star system is Alpha Centauri. But even this simple statement hides complexity. Alpha Centauri is not a single star. It is a system of three. The two primary stars, Alpha Centauri A and B, are similar to our Sun and orbit each other in a stable pair. A third member, Proxima Centauri, is smaller, dimmer, and slightly closer to Earth. From a distance perspective alone, Proxima appears to be the logical first target. But distance is only one variable. What matters more is the environment that awaits at the destination. Proxima Centauri hosts several known planets, including Proxima b, an Earth-sized world located within what astronomers call the habitable zone. This is the region around a star where temperatures may allow liquid water to exist. On the surface, this makes Proxima b an appealing candidate. However, the nature of its parent star complicates this picture. Proxima is a red dwarf, a type of star known for instability. It emits frequent and intense bursts of radiation. Over long periods, this activity can strip away planetary atmospheres, leaving surfaces exposed and inhospitable. A useful teaching insight here is that habitability is not defined by position alone. A planet can lie within the correct distance from its star and still lack the conditions required for life. Atmosphere, magnetic fields, and stellar behavior all play essential roles. This creates a trade-off. Proxima is closer, but potentially more hostile. The larger stars in the Alpha Centauri system may offer more stable environments, but they lie slightly farther away and are more complex to navigate. Even small differences in distance become significant at interstellar scales. A fraction of a light year can translate into years or decades of additional travel time depending on velocity. So the decision is not trivial. In practice, this means that exploration must come before settlement. Early missions would likely focus on gathering data, studying planetary conditions, and confirming whether any of these worlds can truly support life or human presence. Only after that knowledge is secured can long-term planning begin. So the choice of destination is not simply a matter of selecting the nearest star. It is a careful evaluation of risk, reward, and survivability. And once that decision is made, another layer of complexity emerges. Even with a suitable destination and a capable spacecraft, one question remains unresolved. How do humans endure a journey that may last longer than their own lifetime? And even if the destination is chosen with care and the spacecraft is designed with precision, one challenge remains that cannot be solved by engineering alone. It is the challenge of the people who must make the journey. Interstellar travel, especially at the speeds we have discussed, is not a short expedition. It stretches across decades and in some cases across generations. This changes the nature of the mission entirely. The crew is not simply traveling, they are living their entire lives within the confines of the spacecraft. A useful way to understand this is to shift perspective. Imagine not boarding a vehicle but being born into one. For some individuals on such a mission, the ship would be the only world they ever know. This introduces psychological dimensions that are difficult to measure but impossible to ignore. Isolation becomes a constant condition. Unlike missions within the solar system, communication with Earth would involve delays measured in years. A message sent home would not receive a response within a human conversation timescale. In practical terms, the crew would operate independently, without real-time support. There is also the question of continuity. Over a journey lasting more than a century, generations would pass. The priorities, values, and even the identity of the crew could shift over time. Maintaining a shared purpose across such long durations becomes a complex social challenge. A teaching insight here is that systems involving humans are not static. They evolve. Any long-duration mission must account not only for physical survival, but for cultural and psychological stability. Biology adds another layer. Extended exposure to space conditions, even in controlled environments, may affect human health in ways that are not fully understood. Life extension technologies or stasis could reduce some of these risks, but they introduce new uncertainties of their own. And then there is the most fundamental question. What does it mean to commit to a journey with no guarantee of return? For many on board, Earth would become a distant point in history rather than a place they expect to see again. This is why the human factor cannot be treated as a secondary concern. It may in fact be the defining one. A spacecraft can be engineered for reliability. A society must be sustained through cooperation, purpose, and adaptability. In this sense, the success of an interstellar mission depends as much on sociology and psychology as it does on physics and engineering. And once we recognize this, the broader picture becomes clearer. If humanity can overcome not just the technical barriers, but also the human ones, then the final step is no longer a question of possibility. It becomes a question of time. And when all these challenges are placed side by side, the engineering, the economics, the human limits, a natural conclusion begins to form. Not that interstellar travel is easy, but that it is ultimately achievable. Given enough time, a civilization that continues to expand its knowledge and resources will reach a point where such missions become feasible. This is not a sudden breakthrough, but a gradual accumulation of capability. Each advancement in energy, automation, and space infrastructure moves the boundaries slightly further outward. At higher velocities, the nature of the journey changes once again. If a spacecraft could reach even 10% of the speed of light, the distance to Alpha Centauri could be covered in roughly 40 years. For the first time, the journey begins to fit within a human career span. A useful teaching insight here is that small increases in velocity, when measured against the speed of light, produce large reductions in travel time. The relationship is not linear in its impact on human planning. Crossing from 1% to 10% of light speed transforms the mission from generational to personal. This shift has profound consequences. It allows for direct participation, continuity of knowledge, and a clearer sense of purpose for those involved. The journey is no longer something passed down across generations, but something that can be experienced within a single lifetime. But the significance of the first successful mission goes beyond its duration. It marks a transition in how humanity relates to the universe. Until that point, we remain a civilization bound to one star system, no matter how far we travel within it. The moment a spacecraft successfully reaches another star, that boundary is crossed permanently. It establishes that the distance between stars is not a barrier, but a challenge that can be overcome. From there, the pattern becomes clear. What is done once can be repeated, improved, and expanded. New missions follow, technologies advance, and the network of human presence begins to extend outward. A simple comparison can help clarify this transition. The first ocean crossing did not connect every continent, but it proved that such connections were possible. Over time, routes multiplied, and what was once extraordinary became routine. Interstellar travel would follow a similar path, though on a far greater scale. And so, when that first ship finally departs, it will not only be carrying people or instruments, it will carry a new definition of what it means to be human. Not a species confined to a single world, but one capable of moving between the stars. At that point, the journey to Alpha Centauri is no longer the goal, it is the beginning.